Hi YouTube, I'm Andy, welcome to my shed. Today I'm going to be building a new LED matrix like this one. This is a prototype I built a few months ago now. It's 22 by 6, that's a total of 132 pixels. I'm using RGB LED strips, WS2812, also known as NeoPixels, and it's controlled by an Arduino. And this was a very kind of quick and dirty prototype really to try out some ideas and see what works and what doesn't. So I'm now planning to build a bigger and hopefully better version, which will be 24 by 18. That's a total of 432 pixels. So I thought we'd start by taking this one apart. We'll do a bit of a big Clive job to see what's in it. Talk about some of the problems that I encountered and some things I think can be done better for the next one. And then we'll look at designing the new version and applying those lessons that we've learned. So this is the back of the unit. As you can see, it is a bit rough, not really very well finished. But for a test model it's fine. I'm going to disconnect this and then just take you through the wiring. So this is the DC voltage in. Currently I'm powering this from my lab bench power supply, running it at 12 volts. It goes through this power distribution board, which then feeds these three buck converters. These are based on the MP1548EN chip. And that will take anything from, in this case we want 5 volts out to power the LEDs, so we have to give it at least I think about 6 or 7, and that will take up to 28 volts is the maximum rated input voltage. So we've got a wide range of inputs we can give it, and it will give a steady 5 volts output to drive the LEDs. On each output we have a 1000 microfarad capacitor just to smooth the voltage out, as per the recommendations of the NeoPixel Uber guide. And then each buck converter feeds 2 strips of LEDs through the red and black wires. The buck converter at the bottom here, this also has 5 volts going out to this connector, which we use to connect the Arduino. And then the Arduino's the third line here, a blue wire, which is the data wire where the Arduino sends data back down this wire to control which of the LEDs are switched on and off. And so this blue wire runs down to the first strip of LEDs, data runs across here, at the other end we have a small connecting wire which connects the data line to the next row, which then runs back this way. There's another connector here to the third row, connector here to the fourth, and so on. So that's how the data gets across the whole array. I've also got in here some arcade buttons on the end, which I put in really just for testing, and you can also see the bad paint job I did there. So I was using these just to switch between patterns, and there's some status LEDs there as well. Each pixel has a red, green and a blue LED. Theoretically they can draw 20 milliamps each, giving a total of 60 milliamps per pixel, but in practice I've found that it's closer to about 45. So if we use 50 as a rough guide, we've got 22 pixels here, that gives a total of 1.1 amps per row. They're all on full brightness white. So 2 rows 2.2 amps, these are rated at 3 amps at 5 volts. Whether or not I'd actually trust them to run them fully at 3 amps, I'm not sure, but we have got a little bit of a safety margin there. So this part here, I call this the back plane. I'm just going to try and force it out now. This is in quite tight. This is constructed from 7mm MDF that has a white melamine face on one side. So you can see I've cut little slots in the end here for the LED strips to feed through. A little bit of hot glue on the back there just to hold everything in place. It's cheap, it's easy to cut, although you do have to be careful when cutting MDF because the dust is rather nasty. But you can see one of the problems here, that this has already started to warp. It's quite flexible, and MDF will absorb moisture and expand, whereas the melamine side won't, so it has this tendency to bend. I've also got problems with the end delaminating here, partly from where I've been wedging it into the case and trying to pull it out again, and also where I put a screw through to try and yank it back out again. So I wouldn't recommend using MDF for anything except a very basic test model. Inside the case here we have the dividers. These are made from foam core, foam board it's also called, and these have been cut with little slots that just mate together to create the dividers. Now you can cut these with a scalpel or an X-Acto knife, but obviously it takes a lot of time because there's lots of slots to cut. So I built a jig and used my table saw to cut these, and that worked really well. Very quick, very easy once I've built the jig, so I'll be talking more about that in another video. And in the case here, this is made from 12mm MDF, that's around ½ an inch, but as you can see it's quite flexible. It's not really strong enough for a case of this size, particularly if I'm going to make a bigger case. I'm going to need something better than that. The other thing about MDF is it's not very nice to paint. It's not too bad on the flat surfaces, but the end grain is a real mess. It needs lots of filling and sanding to make a nice finish of that. So depending on what you want to use it for, whether it's going to be a decorative piece or just something for fun, you might want to choose something a bit better than that. I certainly will be for my next version. And on the front, you can see we've got a piece of acrylic, I think this is, plasticky stuff, kind of diffused, opaque style. I've actually cut a groove all around the inside of this box here in order to sit the diffuser in. That works quite well. Obviously it means it's permanently attached, but being able to come out the back here does mean you can take it apart and do any maintenance. So, for the new backplane, I'm going to be using this. This is a sample piece I got, and obviously this is black, not white. This is aluminium composite, so it's 2 sheets of aluminium with a layer of plastic sandwich between it. One of the trade names for this is Dibond, but there's various other names as well. It's really light, really stiff, and with this test piece I did some test drillings just to make sure it was easy to machine and work with, and yeah, it is compared to, that's just some of my bad drilling. The aluminium conducts heat very efficiently, so it should stop any hot spots developing around the LEDs. One thing to be wary of is that aluminium also conducts electricity. Now the paint coating on this doesn't, but as soon as you scratch it or drill through it and expose the aluminium, this will conduct electricity. So with grooves like this, you do need to be careful about filing down any sharp edges before you feed the LED through, in case a sharp edge should cut through the tape and create a short circuit. So I need to work out how large the backplane and diffuser need to be for the new version. So the LEDs I'm using have 30 per metre, which means they're spaced 33 1/3 millimetres apart. So let's draw a very simple example. Just draw 3 LEDs, a centre line down here, and these are on a tape going across here. So the dividers, I won't draw these quite to scale, but they'll be sitting across these centre lines here, and then on the end we'll also want the end panel to come in by a similar amount in from that centre line, so that we end up with all these compartments being the same size. So the back plane here will sit across there, and for front diffuser we're going to cut, so this will be some thicker panel, let's say that's so thick, we have something like that there, and the diffuser will then sit inside that groove. So we know that this distance between these centre lines is 33.3 millimetres, and our foam board dividers are 5 millimetres. So for this simple example, we've got 3 cells, that would be 3 times 33, which is 100 millimetres, going to this centre line. But then for the back panel, we need to bring it in by half the distance of the divider, so that's 2.5 millimetres there, and again 2.5 millimetres there. So overall, we've reduced the width of the back plane, sits inside the side panels to 95, and here with the front diffuser, we've gone half the distance, so 2.5 millimetres outside of the centre line, and again 2.5 here. So we've increased that by 5 millimetres overall outside of that centre line. So that becomes 105 millimetres in this example. Now the one I'm going to build, I'm going for 24 by 18. So I need to multiply this by 33. The easy way to do that is to divide it by 3 and then multiply by 100. Divide this by 3, we get 6, then multiply by 100. So that's going to be our overall dimensions to these centre lines. For the diffuser, we need to add 5 millimetres, gives us 805, and we're adding that in both dimensions. And then for the back plane, we need to subtract 5 millimetres to bring it inside the side panels. So that takes us to 795 by 595 millimetres. So now let's talk about how we're going to power this system. We've got 24 LEDs in a row. Each one we're saying can draw up to around 50 milliamps. So that gives us 1.2 amps per row. So we could continue to use a buck converter rated at 3 amps to drive 2 rows for a total of around 2.4 amps. Now it did occur to me that I could just power the whole thing from a single 5-volt power supply, but we have to consider we've got 1.2 amps per row and we've got 18 rows, which gives us a total of 21.6 amps. Call it say 22. I would probably want to be using a 25 amp power supply, or maybe 30, maybe even more if I want to be really cautious. So those kind of currents are quite a lot to be pushing around a small piece of wire. I didn't want to have to start using really heavy gauge wire to make that work. So I decided to stick with a system that I know, even though it's possibly not quite as efficient. It does mean that I can scale it up quite easily. I just need to have 1 buck converter for every 2 rows, and then find some way to power the buck converters. So if we take, let's take this figure of 22 amps total at 5 volts, multiply those together, and it tells us that we've got a power consumption of around 110 watts. So just to make the numbers easier, let's round that up to 120 watts, and say if we were running that at 12 volts, we divide that into that, and that would require 10 amps, or at 24 volts it would require around 5 amps. Now of course we need to also factor in some inefficiency plus a bit. But as it happens, I've got a 24 volt 6.5 amp power supply here, so I can actually use that to power all the buck converters I need at 24 volts and have them step it down to 5 volts. The other reason why I favour this is that it's a modular system, so I can expand it easily, but also if, for example, we had an LED that failed and short-circuited the system, I don't want it to blow up my one single power supply and take out the whole unit. I would rather it just, say, destroyed a row of pixels or the buck converter on a particular row and the rest of the unit carried on working. So I kind of see these buck converters as sacrificial lambs, if you like. They're fuses that I don't mind blowing because they're very cheap. I think I paid £3.90 for 10 shipped from China, so the equivalent of €5 or $5 US. So the issue then is how we take these tiny little buck converters and wire them all up in a way that's a bit nicer than what we had in the prototype, which looks like this. So I started off with a piece of prototyping board like this and attached 3 of the buck converters like so. We've got the power comes in here, it's fed in parallel to all 3 buck converters, and then we've got 3 separate outputs with a smoothing capacitor, and each one feeds 2 connectors for the LED strips. And you might just be able to see in there's also the blue link wires that chain the data connections together, so I don't need to worry about too much wiring when I'm putting the unit together. So the power in is also connected in parallel to this socket, so that I can daisy chain several of these units together using this pin going into the input pin of the next module, and so on. And then there's also a connection here for the microprocessor, which is feeding off one of these buck converters, I think the middle one. So this took me about 2 hours to make, about an hour to design it and figure out where everything was going to go, and then about another hour to actually connect everything up and solder it and add all these wires on the back. So I'd need 3 of these, and having made the first one and thinking it's going to take me 2 or so hours to make 2 more, I decided instead to design a custom PCB. So I made this using the free version of EagleCAD. Only took about an hour, a bit less than an hour maybe. And then I sent the design off to a company in China called All PCB. I sent it to them on a Saturday night, and the following Thursday I received back 10 boards. In fact, I think they sent me 12, but I ordered 10. And they're fantastic. And the total cost for that was $5 US, including shipping. So I was very pleased with that, and it then meant I could very quickly populate the boards to make these power modules. So I actually made up the 2 modules in less than an hour. So overall I think I saved myself time over making prototypes like this, and I've got a much nicer result at the end, and a whole bunch of these boards spare for other projects should I need them. So I've ordered the aluminium composite for the backplate, I've ordered the acrylic for the diffuser, and I've got my PCBs for making the power modules. So I'm all ready to go now, but it's getting a bit cold in my shed. It's the middle of winter and the sun's going down, so I'm going to call it a day for this video. But in the next video we'll be looking at the construction of the backplane, so marking it up, drilling holes, attaching LEDs, and then wiring it all together. In the 3rd video in the series we'll be looking at the construction of the case and the dividers that divide the cells up, including how I made the jig to cut them up easily and quickly on the table saw. And then in the 4th video we'll be looking at the software, the firmware used to control the LED, and also some software I've been working on to help design and generate interesting patterns to run on it. So I hope you've enjoyed it today, hope you've learned something interesting, and hopefully I'll see you again. Thanks for watching.